Okay, let's look at the first example, which is a very specific kind of a renewal chain. We've seen these renewal chains before, and we've even computed their stationary distributions, which sometimes don't exist. And so I've baked this example a little bit to make sure that the stationary distribution does actually turn out to exist, or at least we can compute it easily. So let me just kind of recall again, what are these renewal chains about, right? The prototypical example, and maybe I've discussed this already, is this example with a light bulb, right? So the man goes to the store and gets a light bulb, and that light bulb, maybe has some defect and only works for, some number of days, like n days. And so, and after n days, the light bulb goes out, right? And the man has to go to the store again. And so this is what this chain is representing, right? At time 0, we have this, we kind of are purchasing this brand new light bulb, and we have a transition from 0 to out to some natural number with this probability, right? So these are, you can try to make sure that the probabilities here do indeed sum to 1, right? It's pretty important to ensure that, right, the transition from 0, and this is overall states x, is going to be of this form. And so if you sum this over 0 to infinity, right, this is going to be a geometric sum, which is going to give you 1, right? So the problem is at least set up well set up, and you can verify this on your own. But these are the probabilities that determine the length of time that the light bulb is going to remain operational, right? So it goes out to state n, and then once it hits state n, it in a deterministic fashion, right, probability 1, right, it just goes tick, 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 it goes all the way back to 0, right? That's these probabilities here at work. And so, and this process repeats itself, right? Once the light bulb, goes out, right, man goes to the store, right, we generate a new lifetime of this light bulb, maybe it's 4 days. So after 4 days, right, the light bulb is out again, which it's a very bad light bulb apparently. So obviously I guess you can set up these probabilities to be a little bit more believable maybe than what I've done here, right? It's depending on what Q is also it's going to be either realistic or there's going to be some kind of crappy light bulbs. Okay, so let me get back on message here, right? So we've computed the stationary measure and the stationary distribution of this in general, right? So the stationary measure was given by this expression. You can review that video clip again if you want to recall how that's done. And here this is just simply plug in, right? So I'm going to start off with the fact that we've already obtained this expression here, and I just plug in, right? I just write that in, then rewrite this infinite sum by taking out the qx. The reason I do this is to set up a geometric sum that runs from 0 out to infinity, right? So this is q, that looks like a typo, that's a q raised to the nth power, right? So that looks more correct. And you can verify that, right, there's an equality here. This is the same exact expression, and then I've done this so that this geometric sum obviously converges to 1 divided by 1 minus q, and so all I get is q to the x. And then my stationary distribution is this guy right here, mu x over the sum over the mu's, and here I've baked the cake so that this thing converges, right? The sum of this overall possible x from x equals 0 out to infinity is again 1 divided by 1 minus q. And that's exactly how this popped up here, right? This is used to be in the denominator as 1 over 1 minus q, and then it went upstairs. So you have a well-defined stationary distribution here, and we can even start constructing the time reverse chain in this case. But before we do this, let's try to explore a little bit sort of what the intuition is telling us, right? So the question is this process time reversible, right? Is it a reversible process? And you can kind of sometimes with these examples get yourself in trouble, but basically here, right, in some sense you're watching a video of the man going to the store, getting the light bulb, and then we wait and the light bulb seems to be operational, and then all of a sudden it goes out, then man goes to the store again, and if you kind of watch the video backwards, you clearly see that something is suspicious is going on, right? Because in one case, you know, the man's going to take the light bulb from the store and bring it home, and you know, when the video is backwards, it looks like he's taking a working light bulb and then bringing it to the store for some unknown reason, right? So this already, you know, the story kind of breaks down, and it looks like you'll be able to tell from the video whether time is going forward or backwards, right? So at least that seems like a reasonable guess that this chain is going to be irreversible, right? You can detect that you know, if this video of this is being played backwards, you'll kind of be able to spot this. So you know, that's the quick answer, right? But just using your intuition. But you know, we also have to be you know, a little bit careful. Well, let's see what the kind of the math says. So the math says that, you know, first thing we want to do is try to see if you know, what the, let's say, time reversed chain looks like. You know, one thing you can do is try to verify local balance, which we kind of, I think, already know in this case that it's not going to hold from a previous lecture. But let's suspend that you know, for a second. We say we don't know that. Let's try to see what the actual time reverse chain looks like, right? What are the probabilities that appear to kind of guide the sort of, you know, if the video that we're looking is played backwards, right? What are the probabilities with which kind of this process is operating? And you know, you can kind of go through and try to kind of substitute you know, different values, but essentially you start out with the p prime xy, right? And then, you know, you write down, this is by definition what the transition probabilities of the time reverse chain are. And you know, here, right, we know that most of these are 0, right? What are the only times when they're not 0? Well, when y is equal to 0, right, clearly we can transition to any state with that probability. So in the case where y is 0, I would first fill in this part, right, which is going to be precisely that expression up there, 1 minus q times qx. And then the question is, you know, what happens to my qx? Well, I would need to then plug in the pi y over pi x. So what's my pi y? The y is 0, right? And so at 0 you have 1 minus q. And then what's pi x? Pi x is the same thing as this transition probability. So essentially this denominator here just cancels out this for y equals 0. And so you're left with just pi y, which is, you know, pi y when y equals 0 is just 1 minus q times q to the 0. So that's 1 over q. So it's a bit of a long-winded way. But, you know, the key to kind of working through this is just to make sure you don't confuse with the, you know, the order is reversed, right? So here I kind of spotted, you know, what's a nice value of y that I can put here to make things a bit easier. And so I started with y equals 0, and then, you know, I saw that the p0x cancels the pi x, right? These two cancel for this case, and you're just left with pi y, and that's just pi 0, which equals 1 over 1 minus q. And then maybe the slightly more difficult case is the one where y equals x plus 1. And it has to be, right, this is sort of the only way it had to be, right, that these numbers are all essentially going to be equal to 0 unless you're transitioning, right, from a higher number to a lower number. And so I put, you know, y equal to x plus 1 specifically for that reason, right, and that basically sets this to 1. And then the p prime is going to be just the ratio of the pi y and the pi x, right, and the ratio of two successive you know, values of the stationary distribution, right, the ratio of pi x plus 1 to pi x is going to just be q, right? That's the only thing. It's going to be q to the x plus 1, and then the rest is going to divide out, leaving just the q. So, you know, maybe this is, you know, a little bit abstract, but, you know, hopefully you're starting to see kind of what this chain is starting to look like. It's clearly very different, right? So for one, if you want to kind of get to a rigorous proof of why this chain is not reversible, the reason is that this does not equal to pxy, which was the requirement for time reversibility, right? Another way to show this would be to just somehow try to argue that local balance is not met, right? Which we can also do because we have pi x. So you can also try to do it that way. But essentially the two are one and the same. Here I like this approach because we also get the time reverse chain. And what does the time reverse chain look like? Well, it's the same diagram as here, but all the arrows are reversed, right? So you just flip the arrows. That's actually a nice way to get a handle on what the time reverse chain looks like immediately. Whatever transition you drew in your transition diagram, that connecting arrow will still be there. It just has to go in the opposite direction, right? Because time is moving the other way. And so now this chain looks very different. What's actually happening here, right? All of these one-step transitions from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4 are now happening with probability q. So it's sort of like you're at some state and you have probability of q of moving forward, right? So think about maybe flipping a coin, maybe a biased coin that lands on heads with probability q and lands on tails with probability 1 minus q. And in this experiment, what's happening is that you keep flipping this coin, right? And as long as you're getting a heads, you get to move ahead, right? You move one step ahead for every heads. As soon as you get a tails, you move all the way back down to 0, right? With probability 1 minus q, you flip a tails, you move all the way back, right? So this is one of those, you could almost think of what's a good physical kind of process that you could see in nature for this could be maybe like a swimmer like swimming out into the ocean, right? And so there are these waves and they wash them back to the shore, and so maybe kind of gets past a wave with each wave with probability q, but then eventually one is going to get him or her and are going to be washed back to shore, right? And so that could be sort of one example, and you're welcome to think of your own. But clearly the behavior of it looks very different, right? You'd be able to say immediately if you saw either the swimmer going out to the swimming out to the sea and being washed back ashore, or whether you use the light bulb analogy, right? Those videos played forward and backwards would look very very, very different, right? It's the video of the swimmer, right, would first get thrown out, right, into some kind of far distance and then move back somehow, right? So it would look completely different than the swimmer actually swimming forward and then the wave moving him back ashore, right? The waves don't reach out to the shore and grab people and pull them into the depths of the ocean, right? So hopefully you kind of see this and you can try to think of your own examples, right, and play the movie kind of in your head, right, back and forth, and but at the end of the day, sort of the math says what it says, right? That these two quantities are just not equal, right? Q is not, right, this p prime xy does not equal to this, right? This is going to be 0 for a transition that goes from little x to x plus 1, right? And q does not equal to 0, and therefore in this specific sort of version of a renewal chain, there is no reversibility at all, right? There still exists a time reverse chain, right? That always exists, right? That's going to be a chain x prime, right? And then the original renewal chain is the Markov chain x, but they move very differently, and if you saw a movie of either, you'd very quickly be able to spot which direction is time is moving in, or rather which chain you're observing, right? Whether you're looking at the actual chain, the renewal chain, or its time reversed version.